So we're going to use modeling to solve a physics problem. An engineer is determining the type of wire to hang a light in an elevator. The wire can withstand 66 newtons of upward force. The light also has 52 newtons of downward weight force. That's the force due to gravity. What is the maximum upward acceleration before the wire breaks? The lamp's mass is 5.3 kilograms. So we have some elevator, and inside the elevator, the engineer is wanting to put a light. And it's connected by some wire. It's a pendant light. It's connected by some wire to the top of the elevator. What we're told is actually the upward limit of the tension that the wire can experience. This 66 newtons, this is an upward tension force. So I can take this wire and I can turn it into a free body diagram. And the first thing I'm going to draw is this upward maximum that the wire can experience. This is tension, T. It's the pull due to the wire is equal to 66 newtons upward. And it is a vector. We see it's pointing in the upward direction. And we're told also that the light has 52 newtons of downward weight force. So we're pulling straight down with 52 newtons. This is the weight force. And it is less than the 66 Newton upward force. So we have these two forces. They're pulling in opposite directions. So we're going to have some net force. One of these is greater than the other. How do we go from a net force to a maximum upward acceleration? Well, this tension is the maximum upward force. So if we take tension minus the weight force, we get a difference of 14 newtons. So this is the net force that this wire or light is experiencing. And we know from Newton's second law that force is equal to mass times acceleration. So force is proportional to acceleration by this factor of mass. And, well, now what can we do? So we have this net force. Well, we remember that this is actually the sum of all the forces on an object. And isn't that what we've done here? We've taken the tension force, which is 66 newtons upward, and we've added to it this downward or negative force that is 52 newtons. So the net force, F net, is equal to 14 newtons. We saw that when we subtracted them from each other down here. So then the maximum acceleration that this wire can experience is going to be related to F net, because F net takes into account this maximum upward force that the wire can withstand before it snaps. So we simply rearrange Newton's second law for acceleration. We know the total force that the wire is experiencing. We just need to divide that by the mass. So Newton's second law then becomes, if I divide both sides of this by mass, I have acceleration now is equal to the force divided by the mass. And this acceleration is indeed the maximum acceleration, because it's taking into account the upward force that was the maximum upward force that this light can experience before the wire snaps. So we plug in our forces now. So this becomes now 14 newtons divided by 5.3 kilograms. And what we get here is, plugging that into our calculator, we get 2.64 meters per second squared. Again, if you're not sure where this came from, where the meters per second squared came from, is what you need to do is you need to take the units here and resolve them. So a Newton is equal to a kilogram meter per second squared. And you see it's divided by kilograms, so we then divided newtons by kilograms, and that gets us the unit of acceleration, which is what we want. So this 2.64 meters per second squared is the maximum acceleration that the wire can experience before it snaps. This acceleration and this force are directly related. You can talk about the wire snapping due to the force, or you can talk about the wire snapping due to the acceleration. The only thing we have to add then is well, what direction is this acceleration? Well, this is an upward acceleration. It's pointing upward because the net force is pointing upward. We had more upward force than we had downward force.